want to learn calculus fast? Many people, they want to learn calculus independently of their bad experience with mathematics or calculus. That's why I decided to start this new series of videos about learning calculus fast. And this is the first lesson. So I need two things: motivation and engagement, and one more thing: commitment. I'm going to commit the time to provide you with what you need to know to understand calculus and to be able to answer calculus questions. This is the beginning of the journey. I want to be specific enough for you to understand everything in a lecture in a very brief time, and you will be able to learn, to understand, and what is important, you will be actually answering calculus questions from tests. Welcome to Learning Calculus Fast, and today's lecture is limit. We have to start with limits. Let's see it. What is limit? Limit is a very interesting concept. It's about the behavior of the functions around a particular point x or a particular value. Remember that we have functions everywhere. I don't want to talk about the prerequisites for calculus every time that I'm trying to explain, because the idea of this course is that you learn fast calculus. I invite you to check my podcasts about the calculus prerequisites. It's very interesting. It's about the behavior of a function around a particular value. How the behavior of the function is around a particular value. I invite you to read these questions along with me. We have the following scenario: finding the limit of the function f when x is approaching to 4, and you see a negative at the top, that means the left. So I'm going to help you with the notation first. If you're finding the limit, this is the structure for limit, and the x is approaching to a certain value. That certain value in this case is 4, and they put a negative right here. What they mean is that you are going to check the behavior of the function from the left of the point. If they use 4, x approaching to 4 from the right, they will use the following notation. Okay? I'm assuming that you don't know calculus, and I'm assuming that you do not remember calculus. So you have this notation: limit x approaching to 4 from the left and x approaching to 4 from the right. So, but look, go back to the questions. Involves checking the y values, the f of x values. Remember, another important thing, f of x is equal y. Okay? So x is the domain, f of x is the y, is the behavior of the function. As x approaches 4 from the left, I highlight it. And I want you to check the table here, because I want to see numerically what is the limit. Limit is about approximation. So we have the values around the point 4, okay, and we have the values of y around the point 4. Take a look here. We have 3.9, we have 3.99999, and we have 3.1234569. That means that we are approaching to 4 from the left. So keep in mind the number system. So we have here the number system, and we have 4 right here, and we are approaching 4 from the left. Okay? That's no means that we're going to use negative numbers. It's just approaching to the numbers closer to 4. When we evaluate the function, this is the results: 1.19, 1.01, 1.00199, 1.30, 1.40, 1.560. We notice that the function is approaching the y value, the f of x. The f of x is approaching to 1. Remember that we have a relation here between x and y. So we are approaching to 4, which is an x value from the left, and we're going to get results of the functions, the y values, the output values, right on top or bottom. I don't know where the function is. We have no idea how that function looks like. So when we have that situation, we can say that the function is approaching to 1. But what is the concept of the limit? The behavior of both sides. Okay? So we have to check what is the behavior of the functions near to 4, both from the right with the positive sign right here. So if we use a table of value, we can see, look at the first scenario. This is from the left, 3.9, 3.99, 3.99, 3.3000 nights, and the function is approaching to 1. But look at the second scenario right here. The second scenario here, we are approaching to 4 from the right, and you can see the positive on top of the 4. So try to keep up with the notation and try to keep up with the idea. When we use tables of values, we can have a better idea what is going on. So we are approaching from the left and we are approaching from the right. Look at the x column, 4.1, 4.01, 4.001, and it's clear that the values are getting closer to 4 from the right. And look at what happened with the y values, the output values. So they're going to be approaching all the time to negative 20. You can see here the negative 20. They are approaching until they get almost 20, negative 20. So we have a problem here. The limit does not exist. And usually in a test, you will see the word, these 3 letters, D and E. That means does not exist. Why the limit does not exist? We have a function here that is behaving differently from the right of 4 than from the left of 4. So we have a function that is moving up to 1. Imagine the coordinate system. And we have a function that when it's approaching from the left is going to 1, and when it's approaching from the right is going to negative 20. So we have something like this. Do we have limits in those cases? No. This is important. Limit by tables, because visually and numerically and arithmetically, we can see the behavior of the function and we can determine if the limit exists or not. Let's see the following example. We have another function f. We have the graph of that function right there. And notice the notation I highlighted in red, x approaching to negative 3 from the right. Okay, look at the arrow here. I'm approaching to negative 3 from the right. And on the other side, I'm approaching, you can see the same behavior. Look at the same behavior right here. The same function f approaching to negative 3 from the right. And we notice that when we are approaching to negative 3 from the right, follow this point right here. Look at the coordinates. The coordinate is moving and moving and moving. And you will also see right here on the screen the motion of the point when it's getting closer to negative 3 from the right. And you notice that the function is approaching to negative 1. Okay, this is one side limit from the right. What happened from the right? It's important that you have clear the following idea. It's not important what happened at that particular point. What is important is what happens closer to that point, near to that point, in the neighbors of that point. This is something that I want you to, that decide to refresh your calculus classes, or this is your first time learning calculus, that you understand that the limit, the idea of the limit, is not important what happened right there at the point x equal -3. Look at more examples right here. So look at the graph of the function f of x. I invite you to see it. And they want us right here to find the limit of the function f when x is approaching to -4. In general, they want the limit. They don't want the two sides limit first. They want just the limit. But you, when they ask you that, you are responsible to find the behavior of the function closer to -4 from the right and closer to -4 from left. And remember, it's not important what happened with the function at x equal -4. If you get a close look right here, you notice that -4 right here, the function is approaching to 7. I have 7 right here. The function is approaching to 7. The y values, the f of x values, that represents the y, the output, they are approaching to 7. This is from the left. And from the right, they are also approaching to 7. So we have a limit here, because the behavior is not like the first example, that one was approaching to 1 and the other one approaching to -20. So the two sides limits are different, so we don't have limit. The limit does not exist. But right here we have a clear limit. The function limit here when the x is approaching to -4 is 7. Look at the example right here. On the right, they want the limit of the function when the x is 7. Let me put a bigger here. Of the function f of x, and this is the graph of the function. So I locate 7 right here on the number line, and I will be approaching from right and from left. But when I approaching from right and from left, we are approaching to the same y value. The same y value here is -5. It is important what happened at the point x equals 7. No. This is not a matter. It's not our business right now. It will be our business later on when we introduce the next concept in calculus, which is continuity. But right now, we don't care about that. We are just finding the limit of the function. Let's see another example here. Another example here. The limit of the function f, we have the graph of the limit right there, and we can see that they want us to find out what happened with the function when the x is approaching to -2 from the left. So you locate -2 right here, and you check what happened when the x is approaching to -2 from the left, from this side. So you notice that the function is approaching to 5. And from the right, 2 plus. 2 minus is from the left, 2 plus, -2 minus is from the left of -2, and -2 plus is from the right of -2. So when you approach it from the right, you will see that the function is also approaching to 5. So we have a limit here. Yes, we have a limit. So both functions are the same. Both limits are the same. The right-hand limit or the left-hand limit, they are both equals. Yes, we have the function, and this is the notation. Since the limit of the function f from when the x is approaching to -2 minus, -2 minus is from the left, is equal to the limit of the function when the x is approaching to -2 from the right, are the same. The limit of the function is 5 when the x is approaching to -2. This is limit using tables, visually understanding, and this is limit using graph. So let's see. We have more examples right here. Look at this interesting example. we have the function f of x right here on your left. And the point here is x equal -2. So look at the location of x equal -2. And notice what is going on here. When the function is approaching from the left to -2, look at what happened with the function. It's going to infinity. It's going to minus infinity. Okay, it's going to minus infinity. Is this what you see here? When the function is approaching to -2 from the left to minus on top to -2, the function is going to minus infinity. This is minus infinity. This is infinity along the y-axis. This is infinity along the x-axis. This is negative infinity along the x-axis. And look, when you check the limit of the function, when x is approaching to -2 from the right, the -2 plus, we notice that the function is going to infinity. So we have here something like this, something that is going down, and later on you will see that this is because the function has an asymptote right here in the middle, passing by x equal -2, but we're going to talk about that later on. That when the function is approaching to -2 from the left, goes to negative infinity, and when the function is approaching to x equal -2 from the right, is going to positive infinity. Situations like this, the right side limit is different from the left side limit. What is the answer? D and E. The limit does not exist. Very interesting. And look at this, what I put here. I evaluate the function for -2. I said earlier, and I keep saying, that what happened with the function at x equal -2 is not important. I said that. But I'm saying that I want you to introduce, by curiosity, what happened with the function, with the y value, with the output value, when the x is -2. The function is undefined. We don't have an actual output value when the x is equal -2. And this is what is called in mathematics undefined. So we don't have a function value, we don't have the y value, we don't have an output value, we don't have a dependent value when the x is actually -2. And we say that the function is undefined for that particular value. What do you think? Tell me now. Now let's move to algebra. Okay, we explore limit using graph, and now we're going to explore limit using algebra. And this is another part of the topic that I want to go over in lecture 1. For the function f of x shown below, determine the limit of the function when the x is approaching to -4. Okay, this is what is called a piecewise function. Why a piecewise function? Because it has two different behavior. One, when the x is greater than -4, is a quadratic function. Look at over here. Prerequisite quadratic functions. Prerequisite quadratic functions. And the function behaves differently when the x is less than -4. It's behaving like a linear function, 3x plus 6. We have a linear function and we have a quadratic function. Prerequisite linear function. Y equal mx plus b. The slope is 3. The y-intercept is 6. This is a parabola. The yellow is opening downward. Why? Because the coefficient of the leading terms, x to the second power, is negative. This is opening downward. Okay, all of those prerequisites, you can take care of them. I can take care also. I can create videos about prerequisites. Just write it down. Write it down if you need videos about prerequisites. Actually, classes about prerequisites. Quadratic linear function. This is what is called a piecewise function, because that behavior, okay, two functions. It's important right here what happened at x equal -4. It's really important here? What happened here? No. What I like is what happens to the right of -4 and from the left of -4. And I have that information. And with that graphing idea, I can move that graphing perspective to algebra. So let me find the limit when the x is approaching to -4 from the left. And we are summarizing the lecture right here. So I'm putting the negative on top of the -4 because I want what happened from the left. From the left, the function f is a linear function, 3x plus x. Okay, less than -4 from the left. If you have problem, you just draw the number line right here. And put -4 right here. From the left, from the right. Right? So from the left, x less than -4. Remember that it's not important what's going on here in -4. The function behaves like a 3x plus x. With a simple substitution, we're going to find what is the left side limit. 3 times -4 plus x. So the limit from the left of -4 is -12 plus 6, which is -6. So I have the left side limit. Let me use a different color. Let me use red for the right side limits, okay, from when the x is approaching to -4 from the right. So let me do it over here. When the x is approaching to -4 from the right plus, the function behaves like this, -x to the second power plus 10. With a simple substitution, we can find the right side limit, minus parenthesis -4 to the power of 2 plus 10. This is -4 to the power of 2, which is 16. With a minus in front is -16 plus 10. The answer is -6. Boom. Beautiful. The left side limit and the right side limit are the same values. The y value is -6 for both. The function behaves like this. It's going to approaching to -6 when the x is -4. So the limit exists and is -6 when the x is approaching to -4, because the right side limit is equal to the left side limit. It's not beautiful how to integrate the table, the graph, and the algebra in only one powerful perspective, and we understand now limit. Look at the piecewise function right there. So the function is approaching to -4. Remember, to -4, that's the point, the x value. The function is a parabola opening downward. Remember that I said that because the minus x squared. This is the minus x squared, the idea of the minus x squared that I want you to have, because as soon as you see more, you understand more, and you learn more, and you learn fast. So this is the reason of the minus x squared plus 10. This is minus x squared plus 10. This over here. By the way, the y-intercept is 10. And this is the reason of the linear function 3x plus 6. This is 3x plus 6. And the limit exists. The limit is -6. And it's -6 because I evaluate -4 from the right and from the left. And I get the same value, -6. This is limit from the perspective of algebra, from the perspective of geometry, the graphing representation, and tables. It's beautiful. It's really beautiful. I have one more example here. If you want more examples, if you want basically a set of questions like the one that we have discussed in this lecture, join the Math Topic membership. And when you join the membership, you will have access to these videos before everyone else. You will have access to the screenshots of these presentations. You will have access to a set of questions with answers of the typical question that we discuss here in the video. So thank you so much. If you join, you're going to have more presentation, more examples, more visualizations, more practice about this. Okay, don't forget, the link is in the description box, and you can join Math Topics membership. Thank you so much if you do that. So look at this. We have to find the limit of the function f of x when the x is approaching to -4. We're going to do the same. And now we have a parabola here, again, and we have a line over here, again. And what happens when the x is greater than -4? From the right and from the left. Okay, from the right is a parabola, so you evaluate the limit. You evaluate the limit. So you will see here the graphing representation when the x is approaching to -4. How much is the y? How much is the x? And then do the same from the left side, approaching to -4. What happened with the y, with the output? They are approaching to the same number. The limits exist in situations like this. This is your homework. Thank you so much. I don't want to extend more. This is the first lecture. If you like lectures like this, please write your comments below. You are the one that decide what will be the next video. I'm planning to continue this series and make you learn calculus fast and with what you need to know. Just that. Thank you so much. See you in the next lecture.